Okay, welcome back. Good morning. Today's course will relatively short, just 6 pages, because at the same time we have another special talk, given by Professor Ye Hua. Okay, so today we will talk about, actually, many students care about the final exam. Final exam covers chapter 10, chapters 10, 11, and 14.123. That means final exam will stop here. Therefore, you can sit back and relax. Enjoy the material I will give you. So I will talk about synchrotron radiation. Chapter 14.4, we will talk about radiation emitted by a charge in arbitrary extremely relativistic motion. In sections 14.2 and 14.3, we examined the radiation problem from the viewpoint of the charged particle. Actually, in section 14.1, we examine the radiation from the viewpoint of observer. And then we switch to the charged particle. Now, switch back to uh, the observer again. Chapter 14.2, sections 14.2 and 14.3, we express the radiation power in terms of instantaneous beta and beta dot. Beta is the velocity divided by the speed of light. Beta dot is the acceleration divided by the speed of light. From here on, from this section, we will switch our viewpoint to the observer again. The emphasis will also be switched from the power of radiation to the frequency spectrum of the signal received at the observation point. So we switch to observation point. One is switch back to the viewpoint of the observer. Second, we switched from the power of radiation to the frequency spectrum of the signal. Okay? To find the spectrum, we need to first know the time history of the observed radiation. That is from the time domain convert to frequency domain. So we need to know the time history of the observed radiation. Hence, we can no longer stick to instantaneous quantity, but quantity we can measure. So not instantaneous quantity in section 14.2 and 14.3. Okay, we must now follow the particle's orbit. As the particle travels along its orbit, it continuously radiates toward the observer. A Fourier transform of the time-dependent signal. So it's a Fourier transform of the time history of the observed radiation. A Fourier transform of the time-dependent signal received length reveal its spectrum contents. We will be interested only in particular acceleration, beta dot perpendicular to beta. That acceleration is perpendicular to the velocity. The reason is as follows. Actually, we have explained why we like this one before, but I will reiterate again. Look at this equation. Equation is 14.27 for a parallel acceleration. We have total radiated power. It depends on the change of P. So it's here. However, for equation 14.47, we know P at the viewpoint of the particle, we have a gamma square. We have a gamma square. And compare with this one. Okay, what happened? Looking from the coefficient, P will be, if we have the same force, so these terms will be the same. Same force. So obviously, gamma square P perpendicular will be gamma square times P parallel for the same accelerating force here. Hence, for the charge with gamma greater than 1 in arbitrary motion, we may neglect this one. And this one is good for acceleration, and this one is good for radiation. For linear accelerator, we prefer this one. For synchrotron radiation, we prefer this one. And so we can consider only PT prime due to perpendicular acceleration. The instantaneous radius of the curvature rho can be expressed in terms of the perpendicular component of the acceleration, v perpendicular dot, as follows. The force is gamma m v squared divided by rho. Gamma m is the effective mass or the relativistic mass. V squared over rho times m is non-relativistic, but we have gamma, so it's a relativistic. So gamma m v perpendicular dot. We can estimate v dot from these relations. Rho is related to, okay, actually you cancel gamma m. We found rho is related to v squared divided by v dot perpendicular component. That's for gamma greater than 1. So since the velocity is very high here, so v equals to c squared divided by v dot perpendicular. Okay. So this slide is a little bit difficult to understand. So take 1 minute break. Let me drink some tea. For a synchrotron radiation, the particle move like circular motion, but actually not exactly circular. I will show you the shape of synchrotron radiation, maybe now. Okay, this is the storage ring. We have many beam lines, okay? So it's not exactly circular. It's just, yeah, here is synchrotron radiation. We will use a linear booster to accelerate the charge, and then electron bunches and move in this way. As you can see here, we turn from this direction to this direction, and here the particle will radiate. So it's a beam line here, another beam line, another beam line, another beamline, 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 beamline. For one beamline, we can do the experiment. So it's not perfect circular, not perfect circular. If we circular, we use a perfect circular, then it will radiate all the time. It's not good. So we change it like zigzag, not something like that, something like that. Okay, go back. Okay, so at some point on beamline, we change its radius, we change its directions using perpendicular force. Where is the force come from? Normally, we use bending magnet, dipole magnet, QV cross B. So if we have a perpendicular magnetic field, Q times V, we will change the direction of the particle. Okay, so we use a dipole magnet. Where is the dipole magnet? Oh, here. This is a dipole magnet. And another magnet. This magnet change the direction and provide the perpendicular acceleration. Okay, that's the magnet. Okay, when you study this part, you can compare with real figure or real photos. You will have a better understanding. So we know angular distribution of the radiation is theta square root is approximately 1 over gamma. We can go back here. So we will have a very narrow cone-like searchlight, very narrow, just very narrow from, okay, you will have a very narrow cone-like searchlight. Okay, so the observer is illuminated by light emitted by an arc of length d over rho over gamma. That's the angle. So the arc is d equals radius times angle, okay, corresponding to the retarded time interval. The retarded time emitted at delta t prime rho gamma v, okay, the retarded time, okay, rho v times v rho over gamma v. In a time interval delta t prime, the front edge, that is, the particle move in this way. And here, the particle will emit the radiation, and it will reach the observer. And when the particle emit the radiation at the speed of light, particle also travel at a speed very, very close to the speed of light. So particle is tracing the light. So when the particle here, it will still radiate. Okay, radiate. And particle here will receive the signal from here. And at the middle, it will receive signal from here. On the other hand, if it moves to here, it will receive signal from here. Leading edge and real edge. Okay. So in an interval delta t, the front edge, that's the front edge, that's the real edge. The front edge of the pulse travel a distance d, c times delta t prime, okay? Delta t prime is here, while the real edge of the poles is behind the front edge by a distance. Real edge is behind a front edge by a distance d minus d. D is the tracing, is here, from here to here. So eventually, that means the particle emit from here, it travel to here, and emit from here, it travel to here. D is from here to here, and D is from here to here. Okay? So from this calculation, we know 1 over beta, 1 minus 1 over beta minus 1 times rho over gamma. And this one can be simplified into 1 plus beta over 2 beta, because very close to the speed of light, maybe 9 digit, 0.9999999, for example. So these two very close to 2 cancel, not much difference. Only a smallly changes. And that's rho over 2 gamma cube. Post durations to the observer, T equals L over C. Post durations, T equals L over C. A broad spectrum ranging from, that's the post duration. Actually, not 1 over gamma, but the post duration is not that simple. It's L over C. That's the pulse duration for a single pulse. A broad spectrum ranges from 0 up to the critical frequency. If we have a single pulse, we can perform the Fourier transform. And if the pulse is very, very narrow, something like delta function, then the spectrum will be very, very broad, cover all the frequency. But now the pulse is not like delta function, but a finite length. So the spectrum is also finite. We know the highest frequency will be the critical frequency. Actually, the frequency will be beyond the critical frequency, but that is not very small. So we call critical frequency of omega c equals to 1 over t equals to c over L, c rho gamma 3. Okay, just here. It's proportional to this one. You might wondering what happened to, yeah, don't worry too much. Maybe you should worry about rho over gamma cube, but there is a factor of 2 here, but actually not very critical. I just want to let you know the frequency is actually very, very high. Omega c is the maximum frequency of the appreciable radiation. Very, very high. Very, very high. Just give you another drawing. Synchrotron radiation, we have a quantitative discussion. If the charge is in a circular motion with the rotation frequency omega 0, with rotating frequency omega 0, that means omega 0 times rho over c. Okay, what does this mean? Omega c, so we can determine the rho. Rho will be related to omega 0, gamma to the cube. The pulse occur at the observation point at a regular interval of 2 pi over omega 0. Okay, makes sense. So you can calculate the frequency T0. T0 is a circular motion. It's the circular motion with rotation frequency. But actually, it's not that simple. We have more than one pulse inside, more than one bunch, a lot of bunch, so the frequency will be higher than that. Let's think just one bunch, you can estimate T0. That's the fundamental, that's the period for one turn, one revolution. The pulse of synchrotron radiation propagate radially outward. So from a cornea 10 GeV synchrotron, gamma is very high. Omega 0 is about this value. So omega C will be extremely high, roughly about 16 keV, hard X-ray. It's X-ray. Energy is large enough, that is hard X-ray. Energy is not that high, that is soft X-ray. So obviously it's hard X-ray. So let me show you again. Omega C equals C over rho gamma cubed. The critical frequency, omega C, means the maximum frequency of appreciable radiation, 可侦测的 appreciable, detectable, scale as gamma cubed, which explains the extremely high frequency radiation from a synchrotron. The factor gamma cubed is due to the short duration of the pulse seen by the observer. The pulse is shortened by two effects. One, because the angular width is quite short, okay, of the radiation is very narrow. Only the radiation emitted by the electron over an arc of length d can reach the observer. Thus, the electrons, to the electron, the emission interval is delta t prime, approximately equal rho over gamma v. Second, the electron is chasing its radiation. When the electron emits its radiation, it also moves. Emit the radiation is also move at a speed very, very close to the speed of light. Therefore, let's shorten the pulse. Let's compress the pulse. Instead, it is delta t prime compress the pulse by a factor dt prime. So 1 minus beta t prime dot n t prime, 1 minus beta, 1 minus beta. So we have this effect equals to 1 over 2 gamma squared. Effect 2 is exploited in a device called the free electron laser. Okay, actually we talked about this one before. Okay, from here. Conservation of the total radiated power, and in terms of observer, in terms of radiation, in terms of the particle. Okay, pretty good. Last slide. Uh, as a particle, as a practical example. So here I will give you an example to calculate the frequency again. The pulse duration to the observer, consider again at the cornea 10 GeV synchrotron, for which we have omega c equals 2.4 times 10 to the 19th per second. since omega c is 1 over t, the pulse duration t of a single electron is incredibly short, extremely short. This explains the broad spectrum. However, the actual pulse in a synchrotron does not come from a single electron, but from a electron bunch of finite length. Keep this in mind. From an electron bunch. This electron bunch consists of many electrons. Therefore, each electron in the bunch radiates incoherently, so the spectrum of the bunch is the same as that of a single electron, but the pulse duration equals the passage time of an electron bunch. For example, for a bunch length of 6 millimeter, we have a tau is much more shorter. Okay, much more longer compared with this one. That means the electron bunch just not one electron, but a bunch of electrons. And each bunch we have many electrons. That's the first one. And for a synchrotron radiation, we have multiple bunches, more than one, a lot of bunches. Not just one, more than one. Therefore, the frequency can be much lower. Well, with this effect, the critical frequency will be lower, and with the multiple bunches, and the frequency can be lower frequency, omega 0 can be increased. Therefore, we can provide broadband frequency. It's still good enough for many observations. All you need to do is filter out. You have a frequency of very broad spectrum, so you need a filter to select the frequency you want. Okay, just like a bandpass filter. How to do that? You have many techniques. Okay, so I will stop here. Next time, I will give you some example about the synchrotron radiation in Taiwan. Okay, stop. See you next time.